Okay, let's begin. Let's jump right in where we stopped, where we dropped off, which I believe the last thing I did was I drew the graph of the inverse sine function. So maybe let's do the inverse cosine function. So there are really three that we tend to care about in Calc 1. The inverse sine, the inverse cosine, and the inverse tangent. You can have inverse secants and cosecants and cotangents, but I tend not to ask about those. Once you know how to do the sine, the cosine, the tangent, dealing with the others are very similar. So, and in some cases, knowing how to deal with the secant is going to also help, but I'm not going to look at the inverse secant. So, you know where we left off. So, you should remember the cosine graph. This maximum value 1, minimum value -1, does not pass the horizontal line test, so it's not a one-to-one function. What we do here, how we slice the cosine, is we restrict the domain between 0 and pi. So we take this part of the function here. That part of the function, if I consider this the domain and that the codomain, that is one-to-one and onto on that range, then I actually want to find the inverse. So what I'm going to do is I'm going to reflect this in the line y equals x. Flip it. So this is y equals cosine x. This leads to y equals the cosine inverse of x, or sometimes we call that arc cosine. Because a lot of students always mix up the -1 power with 1 over. It does not mean 1 over. That's just notation for the inverse. So basically what you get. So remember, the x's and y's are going to switch places. So you would have the x's, instead of going between 0 and pi, you would have the y values going between 0 and pi. And the y values going between -1 and 1. So now the x values are going to go between -1 and 1. And if you kind of flip that over the y equals x, you are going to get, that's going to be the point, and that's going to be the point. And it's going to look like this. Yeah, a graph that looks like that. It's the cosine inverse graph. Notice that it will only give outputs in a certain range. Note, cosine inverse of x, it will only output values that will be between 0 and pi. And its domain is -1. That's another important kind of function that we want to know about. Can also do the tangent. Remember the y equals tangent graph. That has a bunch of asymptotes that it cannot touch, vertical asymptotes. They occur when the cosine of x is 0, because you're dividing by 0 at those points. The graph cannot exist at those points. You should remember that cosine is equal to 0 at all odd multiples of pi over 2. So pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, etc. Minus pi over 2, minus 3 pi over 2, minus 5 pi over 2, etc. And the tangent graph looks like this. That's that pattern, and it actually keeps repeating that pattern in between all these asymptotes. Again, it doesn't pass the horizontal line test. What we mean for the arctangent is we take the middle piece. So we care about this piece in particular, we single that out. That is 1-to-1 and onto. By the way, it's onto the entire real line. Every single y value will be hit. So look at the line y equals x. And this will give us a graph of the arctangent. Which is a graph that we've seen before, especially when doing limits, but just so you kind of know where it came from. Basically, to the graph y equals arctangent, which is same as tan inverse. Remember, for the inverse, the x and y switches roles. So before, the x's were bound between minus pi over 2 and pi over 2. Now the y's are going to be bound between minus pi over 2 and pi over 2. And if you reflect that, it's going to look like this. That's the graph of the inverse tangent. Now, we want to know how to differentiate functions like this. These functions in particular, but in general, how do you go about differentiating an inverse function? That was the goal. These are just some special mentions here. And I believe I told you everything else I wanted to tell you about inverse functions. Of course, you would have done that in algebra and pre-calc class, so you know a lot more about inverse functions than I already told you. And it's going to be kind of assumed that you know everything. But let's move on to differentiating the inverse. So we want to be able to ask questions like, what would be the slope of this graph? And basically you say, well, call f and its inverse has a special relationship. Basically, if we take f, evaluate it at its inverse function. This isn't always going to be true for the tangents because of the restricted domain. This only works in the restricted domain for the trig functions. But if you take f of f inverse in general, what we get? X. We mentioned that last time. So here's what we're going to do. We are going to differentiate this So once again, what's going to happen is the chain rule is going to come to our rescue. The derivative of this is going to be what? F prime, leave the inside alone, times the derivative of the inverse function. Derivative of x is 1. I'm taking the derivative with respect to x. And what you notice here is my derivative of the inverse function. All I have to do there is now solve for that. F inverse derivative is going to be 1 divided by f prime of f inverse, whenever it exists. Of course, it doesn't exist when you divide by 0, etc. All the usual precautions. But that's the important formula. This is how we can find the derivative of an inverse. Let's do some examples. Compute the derivative of this sine inverse. So here here's what we do. Set f of x equals sine x. Notice that we want the inverse derivative. So that means here f prime of x is going to be cosine of x. This means that f prime of f inverse of x is going to be, well, cosine of the sine inverse. This means the derivative of the sine inverse of x is going to be by this formula, 1 divided by the cosine of sine inverse of x. Now, normally we don't like that form because when you have a trig function operating on an inverse trig function, we tend to be able to rewrite those as polynomials, or at the very least radicals. How did we go about doing that? Do you remember? Or I did that a bunch in pre-calc. No, you don't remember. Okay, so here's what we would set the inverse equal to some angle, because that is what the inverse will do. When you take sine of an angle, it gives you an output. The inverse is going to take the output and give you back the angle. So this would mean that the sine of theta is what gave us x in the first place. The trick here is to think of this as a fraction, x over 1. Why would you think of it as a fraction? Because you want to do SOHCAHTOA. Basically, you remember that sine is opposite over hypotenuse. So this means you can construct a right triangle with angle theta, where the opposite side is x, the hypotenuse is 1, and then Pythagoras' theorem is going to tell you that this is going to be the square root of 1 minus x squared. So this would mean that the cosine of sine inverse is actually just the cosine of theta, because my sine inverse is the theta. Well, that's just going to be adjacent over hypotenuse. And that's going to be just over that. This means the derivative of the sine inverse function is 1 over the square root of 1 minus x squared. That's something that we know now. So of course that doesn't always work. In fact, it only works on the region that you kind of expect it to, because the sine inverse is bounded between plus or minus 1. This is actually only going to work for x between plus or minus 1. Because your sine inverse can actually accept a value larger than that in the first place. Because that would be like you telling me that the sine of something is going to be a number larger than 1. That's not going to happen. So that is our guide. Okay, you guys do that one quickly, 2 minutes, yes?
So cosine just undoes the inverse of sine? So we said
No, the cosine is going to give us this thing. So it doesn't undo it. These aren't inverse functions. The inverse would just give me x as the result. This doesn't give me x, it gives me the square root of 1 minus x squared. I'm just rewriting this thing in a nicer way using trigonometry. Do that. You guys get an answer yet? Huh?
I know the answer, but I don't know how to get it.
Technically, you'd survive with that. Like, I wouldn't ask you to write this on a test, so you would slip through the cracks there.
I can set the setup for it.
Okay. How do we start?
So we could say f of x is equal to tan of x, and then we say f of prime of x is equal to secant squared x,
Correct?
and then we say the derivative of the inverse of tan of x is equal to 1 over secant squared, parentheses, inverse tan x.
Yeah? Now you want to rewrite that? So how would you rewrite this? Yeah?
We'd say tan inverse of x equals theta.
Set tan inverse of x equals theta. This means that your tangent of theta is equal to x over 1 in particular. So your tangent is opposite over adjacent. This gives you a triangle. Opposite over adjacent. Pythagoras' theorem is going to tell you that that's 1 plus x squared. And so this means that the secant squared of the tan inverse of x is going to be the secant squared of theta. Well, that's just 1 over cosine of theta squared. And cosine of theta would be right, so it's 1 over the square root of 1 plus x squared, squared. It's 1 over 1 plus x squared. So now what we can do, let's go back and plug this in. This means that our derivative of the tangent inverse is going to be 1 over the idea is in the right order. The secant is hypotenuse over adjacent. How did I end up with that?
The cosine is adjacent over hypotenuse. So
Oh, yeah, there. I missed the 1 over.
Yeah, the 1.
I'm like, where is that coming from? Okay. 1 over in here, it was 1 over. So that's 1 plus x squared. And that is 1 plus x squared. That's the derivative of the inverse tangent. And like I said, there are tons of things I'm leaving out here about inverse trig functions, but I do expect you to kind of know them. Everyone's going to expect you to kind of know them. So if I just ask you a random thing like, what is the cosine inverse of minus radical 3 over 2? I expect you to be able to know that, figure that out. Things like of that sort. You should know how to evaluate the inverse trig functions, all that good stuff, know what ranges and domains are for them, etc. Right now we're focused on the calculus. That's kind of something you did in pre-talk a lot. Here's another example. Try that. don't really care if you know these or not, but let me just write them down. So you can't say I never told you. So we saw that the derivative of the sine inverse of x is 1 over the square root of 1 plus x squared. We saw that the derivative of tan inverse of x is 1 over 1 plus x squared. Turns out that the derivative of the cosine inverse is actually the negative of that one. The domains are going to matter. This one's a minus. However, for you guys, what I expect you to remember is just these two. So you need to know those two. The rest, be aware of them, but I'm probably never going to test them. Or you could derive them in pretty much the same way. Let's look at this one. We want to find the derivative of the inverse function at the point 2 specifically. So I don't care about the derivative of the inverse as a formula in general, just at the point 2. Not because it's impossible, but because it could be impossible to find it in general. Which I'll point out where the trouble there might become. But let's actually just get through this example. We know the derivative of the inverse at 2 is simply going to be 1 over f prime of f inverse at 2. Now, f prime is going to be 5x to the 4th minus 3x squared plus 2. And f inverse at 2, how do I find that? How do I find f inverse at 2? Do what? Swap what?
So like whatever you get.
How would you find f inverse of 2? What does f inverse of 2 mean?
The x and y values are.
Don't we just plug in 2 and then do the derivative of that?
Plug in 2 where?
The derivative?
That's f prime of 2. I want f inverse of 2. Is that correct? Right. The input of the inverse is the output of the original function. So this means we want x such that f of x is going to give me the output 2. Now here's where the difficulty lies. Now, remember I told you for polynomials of degree 5 or higher, there is no general formula. So you could actually end up in a situation here where the thing you have to solve for x, it's actually impossible for you to do it by hand. But then I told you that in general, that's not a problem. We can approximate it with all kinds of numerical methods that you could learn in other classes. This one, though, we could actually solve, but I deliberately want to not solve it so that you can, because you just bring that over there, factor by grouping, will actually work. But let's pretend that we couldn't solve it. What's another option? Can you see an x value that would actually work here? 1 would actually work. Now, this is what math people call by inspection. Whenever they eyeball something and they just see the answer, they write by inspection. X equals 1. So, a couple things here that I want to mention. This is pretty much the only situation where you're going to get away with by inspection. Right? I want you to show your work all the time. So on a test, you can't just write down all the answers. Well, by inspection. Like, this is the answer. No, you can't do that, right? You're going to, in this situation, it's okay to say, well, yeah, all right, that's not the main focus of this problem. I can just see that x equals 1 is going to work. Now, the good thing about this is that if a function has an inverse, what that means is a 1-to-1 and onto, which means x equals 1 is going to be the only guide that hits 2. So once you find an answer here, that's the only answer. You don't have to worry about anything else. Because otherwise, talking about the inverse wouldn't even make sense. So yeah, notice that if I plug in 1 minus 1 plus 2, I would actually get 2. So x equals 1. This time you could actually solve it, but there will be examples where you can't actually solve that. So x equals 1. So what that means is the derivative of the inverse at 2 is going to be 1 over f prime of f inverse of 2. But we just found that f inverse of 2 is actually 1. So that's just 1 over f prime of 1. So I'm just going to plug in 1 into f prime, put that in the denominator. And I will have that. So that's actually going to be a quarter. Now the use of this is, of course, something I'm actually going to talk about right after this topic. Right after this example. No, we have more examples. But right after this topic, I'm going to talk again about the idea of using tangent lines to approximate functions. So why would some process like this be useful to us? Well, let's say I have a function, but I also care about what its inverse is doing. Now, the function might be complicated. I can't actually find the inverse. And in general, you can't find the inverse for this one, actually. You can figure out when it hits 2, though. So I care about the inverse at the derivative, but maybe the inverse is really hard to find, so I don't really know what formula I'm going to use to find the inverse. So what I can do is instead I can find the derivative of the inverse at some point. That is going to give me the slope of the tangent line to the inverse function. I can construct a tangent line, and instead of using the inverse function, I can deal with the tangent line of the function when I'm close to the point 2. So that will help us with all sorts of approximations. That's the larger picture. That's the big picture, though. For you, you just actually need to know how to go through a problem like this. So I can give you a function, ask you to find the derivative of its inverse at some point. You should know that this is the equation you're going to use. Finding derivative is something you should be like an expert at by the time you get here. When you get to the point where you have to find the inverse of a particular point, understand what it means to be an inverse. The input for the inverse is the output of the original function. So you set the original function equal to that. Most of the time when you get here, it won't be an equation you can actually solve. So you're going to, by inspection, just eyeball which x value is going to work. Usually it's going to be something that you can catch on to pretty easily in Calc 1. Once you have that, you plug it in here and just compute. So the derivative of the inverse is a quarter. Questions on this process? Or? So the larger picture you don't need to know. I just told you that for your education. But a problem like this is something that you should be able to solve. So for test 2, something like this might come on. There's going to be like a problem where I'm like, oh, here's a function. Find the derivative of its inverse. Blah, here. That being said, let's do a few more derivative examples. Just to get used to the derivative of the inverse trig functions. Y prime. A. Maybe I'll give you some time to actually try that. Maybe 8 minutes or so. So actually attempt doing those. Just wait for me to write the answer on the board. You want to know what you understand and what you don't understand before it's too late. Turn this off till you guys are done. Okay, anyone finish all 4? Anyone finish 3 of them? Finish 3? You finished all 4? Okay. That's good. No one finished 2? You got through 2? Okay. Something. Let's actually do this then. So, we just learned them, so for reference, so let's just put the rules up here. Remember that the derivative of the sine inverse is 1 over the radical of 1 minus x squared. Maybe I would even expand this a little bit, which will actually make these a lot easier. But remember, every time I give you a derivative rule, there is the chain rule version of the derivative rule, which means if I want the derivative of sine inverse of something other than x, that's just going to be u prime over the radical of 1 minus u squared. And if I have the derivative of the tangent inverse of something other than x, that's going to be u prime over 1 plus u squared. Right? Chain rule is always something that you can do, and you can implement that within the rules themselves. So in the first one, you will notice that, well, that guy is kind of like the u. So y prime is going to be u prime divided by the square root 1 minus u squared. That's the answer. Anyone get that? Everyone get that? Did it? Huh? I mean, that's good enough. That's not going to simplify it very much. So it's actually not so bad. That was one step. Let's move on to B. Also not so bad. Threw a 4 here to kind of freak you out, but that doesn't really matter for derivatives. You just leave the 4 alone and differentiate the function. So that 4 is going to stay, and this guy here is like my u. So it's going to be u prime divided by 1 plus u squared. That's it. This one I probably would actually rewrite a little bit. So this is 48x cubed over 1 plus 9x to the 8th. That's our derivative. Huh? You're talking to yourself? Okay. This one's slightly more challenging, only slightly. What do you want to use here? Need the product rule. Just realize that there are two functions multiplying each other. So I want to differentiate one function, leave the other one, then differentiate the second, leave the first. Derivative of this is x. I'm going to leave the sine inverse. Plus, I'm going to leave this and differentiate the sine inverse, which I have the rule over there. It's just going to be u prime divided by the radical of 1 minus u squared. So that's going to be 4 divided by the radical of 1 minus 4x squared. The parentheses are important here. Okay? So if you don't have them, you're just saying the x alone is squared, but it's actually the 4 is also squared. That mistake happens all the time. So really, you should think of this as 1 minus 16x squared. Not really much to clean up here, actually. I mean, this is fine as written, but you can try to write this as 4x squared plus 1. That's it. So product rule still a thing. All the rules that I ever give you, they're kind of always applying the background. We just have new functions that we're doing, the tan inverse and the sine inverse. Okay, so how are we going to find y prime here? Huh? Implicit differentiation. Okay, so how do I differentiate this?
1 over square root of 1 minus x plus y squared times the derivative of x plus y.
No. What's the u here? This whole thing is u, right? What's the derivative of u?
That was 1 plus y prime.
1 plus y prime divided by the radical 1 minus u squared plus y prime equals 2x. Now I just need to solve for the y prime. I can split this up. Or just to make things a little bit nicer, maybe I can just kill the fractions with the LCD. So here I would have 1 plus y prime plus y prime times this radical equals 2x times this radical. So, here my y prime is going to be 1 plus this radical. And I have here, bring the minus 1 over, minus 1 plus 2x times this radical. So now I can solve for that by dividing. That's that. Did you actually get all 4? You got the right answers? A lot of times what happens, you have to realize that hindsight is 20/20. A lot of times I'm going through an example, immediately after I write it down, it's obvious that that's what you should have had, right? Because your brain just works backwards into, oh yeah, I see how this stuff falls from this stuff. When you're doing it on your own though, it's very different. It's kind of how students fall into the trap of, well, I understand everything in class, I don't understand why I don't do well on tests. Yeah, watching me do it is different from doing it yourself, so it's very important. Whenever I give you the option, you definitely want to try it on your own before watching me do it on the board. Because I gave you guys a lot of time, and you guys couldn't finish, but did it seem like I did anything difficult? Right, it doesn't seem that way when you're watching me, right? But you doing it is a different ballgame. So you definitely want to make sure you do things on your own so you really understand where you are and what you understand, what was confusing you about, why couldn't you have gotten all 4 in the time I gave you, right? Where did you get stuck? These are things you should be noticing. Different people get stuck at different places. You need to know where you would get stuck personally. Right? So that's that. So I want to talk about another topic. Not going to be a huge conceptual leap. We're just going to use what we've been doing before, kind of, with tangent lines. Just a different way to look at the tangent line. The topic is called linear approximation. And differentials, these kind of refer to the same thing. I'll tell you where the name differential comes from a little bit later. So the goal of this section using tangent lines to approximate curves, to approximate the outputs of functions. So, remember how this whole game got started. We had this curve, we wanted to know what its rate of change was. We interpreted this as slope. We figured out a formula that gave us the slope of the function. This was the limit as h approaches 0 of f of x plus h minus f of x all over h. By doing that, we could construct what we call a tangent line. So sometimes you have a function doing as you do, call that f of x. And at some point of interest, I could create, assuming the f is nice enough for me to actually compute that derivative limit, I could find a tangent line to that function. Now, here is the setup for this kind of principle. Sometimes we know exactly what's going on at the point of interest. Like if there's a point A where I know what A is, I also know what f of A is, but at some point in the future, x, there's another number, call it x. Now, at x, I don't really know what f of x is. Maybe the function is very complicated. Maybe the function actually doesn't even exist. Sometimes, ever so often, how we can use this tangent line is perhaps this point where we know all the information, we have all the data, that's the present. And the future has not been written. So I really don't even know what could happen after this point. Sometimes you can use a tangent line in that situation to kind of predict what's going to happen. But anyway, suppose there is some point in the future on this function that is very difficult for you to determine. So I don't know what that is. I also don't know what the derivative at this point is. Right? I don't really know anything about that point. The idea is we want to use the tangent line to approximate that point. So here is the setup. The difference between the point that we know, the y value of that point, and the y value of the point that we care about, this is called delta y, the change in the y value. Right? This is if my y is equal to f of x. Now, there's another point that can be of interest that is a lot easier to determine. So let's say at this same point, at this x point, I will actually hit the tangent line here. Now that green point is nice. Before, let's actually talk about what the difference in that is going to be. Now the difference between the change in the original point and the change in the point on the tangent line, we call that dy. This is what's called the differential. This is called the differential of y. Now, there's many interpretations that you can put on this, but for us, what we will interpret the dy as, this is just the change of the function as approximated by the tangent line. So, the actual change in the function is the delta y, but sometimes it's very hard for us to figure out what that is. Maybe the function doesn't even exist in the point where we actually want to figure it out. But I can construct a tangent line at the point where I have all the data, and once I have the equation of a line, it's going to be easy to figure out what the other point is. So I would be able to determine this pretty easily. Okay? Now, of course, the idea is, the closer this x is to a, the closer the dy and the delta y is going to be, right? Like if I'm right here, the difference between the tangent line and the function, not very big, right? So if I'm very close, the delta y is a good approximation for the dy. The dy is a good approximation for the delta y. So that's like uppercase Greek delta. That is just a lowercase English delta, which is a d. There's also a lowercase Greek delta, but we actually use that for something else, so we just use this regular one. Right? There's going to be a point where you start to write your d's like this. That's called 3. So that's when things really get interesting. Okay, so the idea here is dy is a good approximation for the delta y. In fact, that idea implies the following. that idea implies that the y value for the function will be very close to the y value for the tangent line when x is near A. So A is the point where I have all the information, x is the point where I don't have the information. But if the A and the x are very close together, the difference between the tangent line and the function and the difference between the point on the tangent line and the original point and the difference between the point on the function and the original point, that distance, they're going to be very similar. That's the idea. Now, the y value for the function is, of course, our f of x. What does the y value for the tangent line look like here? What is the equation of that tangent line? Well, I know the slope, right? So the slope is f prime evaluated at A. This would be x minus A. So it's m times x minus x1 plus, so we'd have y minus y1 equals m times x minus x1. That's the m times x minus x1. I would add the y1 to both sides. The y1 in this case is going to be f evaluated at A. So this formula is the formula of interest here. It's called the linear approximation formula. And sometimes the right side, we set it equal to, we call the right side some function on its own. Sometimes you think of a function called L of x for a line, and we define it to be f of a plus f prime of a and x minus a. And this function here, we call it, this is called the linearization of f of x near a. So pretty much instead of thinking of the function, the original function itself, I can think of this equation, the equation of some line, in particular the tangent line, close to the point of interest. Let's do a silly example. What's the linearization of sine x near the point x equals pi over 6? So the idea here, sine function looks like that, doing its thing. And where does the peak happen? What's the x value? Pi over 2. That's going to be pi. 3 pi over 2 is 2 pi 0. Pi over 6 actually happens before pi over 2. So there's some point here that I care about. What I want is to find a line that is going to approximate the curve at that point, is the other way that you want to think about it. So what this means is we would just set our a equals pi over 6, and we would use L of x equals f of a plus f prime of a and x minus a. this is going to be the sine of pi over 6 plus the cosine of pi over 6 times x minus pi over 6. And sine of pi over 6, half cosine of pi over 6. And that's the linearization. In fact, that's the equation of this line. So this line has equation y equals 1/2 plus radical 3 over 2 x minus pi over 6. In other words, when I'm very close to pi over 6, instead of talking about the sine function, I can talk about this function. The idea being, if we were to move a little bit out of the way, I can approximate this point on the curve with that point on the curve. One example, a sexy example of where this is used in real life. A lot of times in finance, these models that you use, plays this kind of game. I mean, everyone would tell you, you can't predict the stock market, right? It's right. We don't know what's going to happen. Like something can happen, then the stock is going to drop. Something else happens, the stock right. You can't really predict it. Why is it that Goldman Sachs consistently makes money then, if they're doing something that can't be predicted? They do things like this. See, what's going to happen is they can know about the current position and trajectory of a stock. They don't know what's going to happen tomorrow. They don't even know what's going to happen an hour from now. They don't care. What they care about, what's going to happen 2 seconds from now. Now, 2 seconds from now, you're not going to have a very drastic change. All we have to do, get our computer to find an approximation to the curve of the stock, anticipate where it's going to be 2 seconds from now. Now, for a human being, you can't do anything in 2 seconds. But if you're a supercomputer, trained to buy and sell stocks, you can do millions of trades in 2 seconds. Now, you might be wrong by a little bit, maybe a few cents on the dollar, but you're going to be making money on average. Make a few cents on a dollar millions of times every 2 seconds, where the computer keeps updating the current position and trajectory and then predicts the next 2 seconds. That's how they make money. That's how they predict the future, with things like this. So, now of course, it gets more complicated than something you can teach in a Cal 1 class, but the idea is there. When they come up with a financial model, that's what they do. What is the best kind of mathematical framework to predict where this graph is going to go? Right? Calculus 1, as an idea, provides one way to go about that. So sometimes the function is complicated in the future, i.e., sometimes it doesn't even exist in the future because we're currently in the present, we don't know what's going to do. So what we do is we approximate with something, and it turns out that over a short span of time, drastic things usually don't happen. It usually takes a natural disaster for something to just rapidly change direction. Right? If life goes on as usual, you can predict to some degree of accuracy what's going to happen 2 seconds from now. So that's the kind of idea. Let's actually use this on something that's a little bit silly, but just to illustrate the idea and the power of this method, what I could do. So, example, use linear approximation to estimate the square root of 3.9. Now, applying this idea to doing that, it's kind of like using a nuclear warhead to kill a fly, I understand, but it's just going to actually illustrate the point to you. And yes, you could plug that in your calculator, but you're not allowed to use calculators in this class. Let's see how good an approximation we can get without a calculator. So nothing up my sleeves, just, come on, all hands, okay. We're going to actually find this thing. So here is what we can do. The square root function, I mean, at certain points we know the values very nicely, but in general, you ask someone a random square root, what's square root of 17.9? They're not going to be able to tell you, right? It's a complicated function for our minds to figure out, okay? So here's how we can actually figure this out by hand. It's 3.9 to 100, because I actually did the actual answer, yes. Okay, so here's what we want to do. And a problem like this is definitely going to be on the next test, by the way, for sure. I'm going to ask you something like this. It's coming, okay? No, I'm not hiding anything. You're going to need to know to do this. And I'll probably put it on a quiz as well. So, what you would do is you're going to want to find a function that will model the thing you want to approximate. You want to approximate the square root of 3.99. What is the obvious function to use? Well, the square root of x. Set f of x equals the square root of x. We want f evaluated at 3.99. Now I don't know exactly what that answer is. What I'm going to do is I'm going to approximate that answer using a tangent line. Next, you're going to set the following. I know that if my x is 3.99, so that this here represents the x value we want, what is going to be the a value? That value that's close to that value that I know all the information for. 4, right. So set a equals 4. Okay. So here, this is going to be the x value. So this is the, no numbers are really ugly, but this is the ugly value that we want to know f of x for. So that's how you want to think of your x in this situation. And the a, this is the nice value, close to x, that we already know f of a and f prime of a for. Okay. So there's an ugly value, the thing you want to approximate. There's a nice value, something close to that where all the numbers work out nice, you know exactly what's going on. 4 is that number in this situation. Now we do know the square root of all kinds of numbers. We know the square root of 1, we know the square root of 16, we know the square root of 64, but 4 is the closest one to 3.99, therefore that's what I'm going to use. So now, note, f prime is going to be 1 over 2 radical x. So this means that f of 4 is going to be, f prime of 4 is going to be, what's f of 4? 2. F prime of 4. 1/4. By the way, I'm not writing this down, but you can think of some a strategy being applied here. 1, define your function. 2, determine x and a. 3, differentiate the function. 4, find f of a and f prime of a. 5 is, now we're going to plug it into the formula. Just so you know what I'm thinking in my head as I'm doing this. So this means the square root of 3.99 is going to be f of 3.99. But that's something I don't know, so I'm going to approximate it by f of 4 plus f prime of 4 times 3.99 minus 4. Right? So that's like my f of x. This is f of x. is approximately equal to f of a times f prime of a times x minus a. And it turns out that's something I can actually do by hand. This is going to be 2 plus a quarter times minus 0.01. In other words, that's going to be 2 minus 1 over 400. In other words, that is going to be 800 over 400 minus 1 over 400, 799 over 400. Now, I actually worked this out. You can double check on your calculators if you want, or your cell phones or whatever. But this actually turns up to be 1.997. Wait, no, I didn't do that on my calculator. What is that? Compute that. What I actually computed was the actual answer. The actual answer. It's 1.99749844. Well, that's rounding. It's 3.5 something. What's this number?
1.9975.
1.9975. I was correct up to 4 decimal places with rounding. By hand.
So do we always round to like the nearest whole number? So like if it
Well,
was
you're not going to round at all. I mean, if you're on a test, that's how you leave your answer.
no, like so like say like the question asks for radical 3.75. Do we still use f of 4?
Yeah, you use the closest thing that you know the answer to. In fact, let me leave you guys with another example. Do it for this. Repeat for the cube root of 8.0. You can tell me what would the function be here? Huh? X to the 1/3, the cube root of x. What would your x be? 8.01. What would the a be? 8. Right. 8 is the closest thing to 8.01 that you actually know the cube root of, and it's pretty close. So try that by hand, see how many decimal place accuracy you can get. But here, just to give you an idea, just to go with the previous analogy, right? This is where Goldman Sachs would guess that the answer is going to be. That's what the answer is actually going to be. Sure, they'll lose from this point on, but they're right from this point up to this point. And just being a little right, you can do a lot with that, especially if you can do millions of things at a time. But actually try that. Time's actually up, so we'll wrap up there. Next time I'm going to talk about differentials. There's another way we like to look at this same idea, but I'll talk about that next time when we kind of isolate the dy. Well, we'll stop right there.